So, good afternoon, everyone. Thank you to the organizers of the PKIA. And I would like to get right into the topic, which is on the scalable model-based decentralized applications. So we have various aspects to decentralized applications that we can run on cloud platforms and secure certain properties by the blockchain. So let's get started. I want to start with the state of the art. If you want to run a cloud application, a scalable cloud application, then we would typically use the classical virtual machine on EC2 on Amazon, for example, and there's auto-scaling implemented in them, and there we can utilize horizontal, vertical scaling solutions. So this means that VM is going to get more resources automatically, or we will also have additional VMs automatically. Then we can use Lambda functions, which are independent of the virtual machines. They specify what is actually computed, and then we can deploy on any number of virtual machines, but we are not concerned with the deployment, it's automatic. And then the serverless computing is right now the state of the art, where even more of the workflow between the Lambda functions gets abstracted away. And so what we get is horizontal and vertical scaling, distribution across servers and data center regions, and ideally we have distribution, high performance scalability, and availability. So this means basically a high standard when it comes to scalable applications. But decentralization is the key challenge that is missing. So among technical challenges such as the one I put first, the CAP theorem, which means that we cannot have all the time all the properties, and this is the partition tolerance availability and the capacity is the consistency, excuse me, for all these properties. We can't guarantee them at every time, but this is for the technical issues. What this is really about is the decentralized properties. So centralized architectures of cloud providers, there we depend on their architectures and on the technical infrastructures, and we depend on the organizational structures as well. So the centralized coordination of application executions is limited because we need to have certain trust assumptions, and we have no trust beyond running in these kinds of environments. So if there's an outage, there's been an outage in Google and Amazon data centers several times over the years where large infrastructures went down. So this means that distribution does not necessarily imply that we also have decentralization, and therefore we want decentralization, ideally the distribution and the non-centralized coordination, which is how I see the decentralization for applications. So how do we run such applications? We run them on the blockchain either, or we run them on a combination of cloud platforms and blockchains. And this paper is about extending such an approach, which I demonstrated, which I introduced before. And the research objective here is the extension of this architecture for authentic and scalable distribution, execution, and tracking of applications. So the architecture that is extended, we can see here, and I will not have time to go over it in full, but I will just make a few key points. We see there is a client application which wants to control the execution, and there's an executable model in it. If we go down, there's the cloud platform where this model is run, and on the right-hand side, we can see that it is registered on the blockchain. And then we can go up again to the instance tracking, where the tracking of the execution is facilitated with each execution state. And I will now go into a few details how this is working. So here we see that the model-based specification, it is used instead of a source code of this program, is a state machine model that we see here as example on Amazon step functions. And it uses a JSON syntax where we can specify with Lambda functions. There is other functions, for example, here reading from a distributed message queue, and we transform data, update a warehouse, and so on. And we use this model as a basis because it is scalable and also because it has various formal properties. And now we can use, first of all, this model and start the instantiation. Now the question is, how do we secure the states of these executable states of the execution that we have here on the blockchain? So we move on to the setup we need for that. First of all, we assume that we create a key pair that is public-private keys. If we use Ethereum, then we use their key generation with ECDSA. And then certificate and blockchain domain. We want to couple down the web world, so to say, with the blockchain world. So we will create a certificate and domain. This will be a standard X509 certificate, and we register it using a blockchain domain. So the blockchain domain is going to link specifically the domain with the certificate that exists on the web to an Ethereum address, to a blockchain address. And additionally, it has records we can put, such as the DNS records that are in the normal domain name system. So on the right-hand side, we see there's a text record, and there we can even bind to the URL this blockchain-secured domain name entry. And now finally, we register the client certificate and also create a signature. We can sign using our Ethereum address, and the Ethereum address is the identity we have, and that is then in the signature we can later verify that the blockchain domain and everything we register for the state of the execution, it really was from this initial party that set this up. And we can, of course, have any number of parties taking part in this system. So for the instance states, now we can trigger a state. That means that the cloud platform is going to advance the state, or the client is requesting this advancement of the state, and then the state is entered by the execution engine. We capture the state in terms of the model-based representation. That is one of the advantages of using the state machine model. We can now have one execution state. We can create the hash value from it, and we can secure this hash value on the blockchain. And this securing is done using a smart contract that is implemented, and then using the smart contract and the setup I have shown before, we can link it to the execution protocol that we can see here on the right-hand side. So this right-hand side has several lines. You can see the lines probably on top, and each line represents one state that is registered together with a hash value, which is the integrity security guarantee that this state had occurred. And so we can put this into the web on our web server and then retrieve it securely. So this is going to be registered in the smart contract and published on the web, but how is it going to get verified? So the details for this are, of course, in the paper, but again, this is a brief summary. We subscribe now to this protocol that we have just seen, where every state will be appearing. And now the validation, it has several components. First of all, we have a validation that the state that we get, now it existed before. We retrieve and validate the instance state ID. It's a content-based hash value, and we can verify it using the model-based application, applying it to a hash function, such as SHA-256, and then we get the same ID. The same we do with the model and instance. So we have the state. We have one instance run, which consists of several states, and we have the whole execution model, which defines the program. And then we have also model and instance state verified. Then we verify the blockchain and address that it was created with the initial address that the issuer used. So here it comes into play what I mentioned, that we want to verify the linkage between the web URL where we find the protocol and the states, and the blockchain registration in the smart contract, and the ENS domain entry. And these will be all matched. Again, this is detailed in the paper, the steps for that. And we can now have a bidirectional binding between the web resource and what is on the blockchain. And then we have the instance protocol server certificate known, so that this server certificate is really known for the instance states. It was used to, it was put there to put the instance states there. The certificate was used, is what it means. And the retrieval of this certificate from the smart contract is first performed, and then lastly we verify the signature of it, so that it was signed with a private key initially putting it there. So this verifies each instance state, the instance protocol, and a model with the issuing address and the timestamps. So in conclusion, we have seen an extended decentralized application architecture for executable models on cloud platforms with instance tracking. And what is new in this approach is the web and blockchain-based authentication, which now uses web servers to distribute executable models and instances. Web architectures tend to be very scalable. And this creates notably a binding between web resources, certificates and blockchain identities, which is very interesting in general that we can create this binding because we can make an identity known on the blockchain, we can bind it to a resource on the web. This means we can use the scalable execution on the cloud platform provided by the model-based specification, and this enhances the scalability for data and compute-intensive applications. And lastly, distributed instance tracking on the blockchain, so anyone can follow this execution, and this is the key idea here for making it observable and also verifiable that any other party can see which execution states were reached, and so they can verify that they occurred correctly, and this makes it a decentralized application. And now this architecture intends to be a scalable, model-based, decentralized application. Thank you for your attention.